All right, so now we're going to start looking at a new idea, and it will get combined with Chapter 10, but this will seem pretty new at first. The focus of what we're going to be doing today is to take any function. We're going to approximate any function as a polynomial. So we want to take any function for, for example, right now we want to take e to the x. This is e to the x here. We want to take e to the x and approximate it as a polynomial. In this case, a linear polynomial, or we could approximate e to the x as a quadratic polynomial, as a cubic, as a fourth root, as a quartic. And the idea is we want to approximate functions as polynomials because we can integrate polynomials easily. So let me say that again. We're gonna attempt to approximate lots of functions as polynomials so that we can integrate them easily. And that's where we're going sort of long term to do the integration of. But for now, the focus of today is just how can we take a function and express it as a polynomial. Well, let's start off with graph number one over here, because that's actually something that we've done a lot of. All we've done here is uh, hold on. So for now, we're only looking when x equals 0. We're approximating that function around that area x equals 0. So you can see, it works while x is close to 0, but not afterwards. So these are approximations around the point x equals 0, limited to that region. Um, so in graph number one versus graph number two, in graph number one, all we've done really is a tangent line approximation. We're drawing a tangent line at x equals 0. And so we know how to draw a tangent line. We know this um, degree 1 approximation. Because to draw a tangent line, we first have to find f of 0, which is e to the 0, which is 1. And then we have to find the slope at that point. So we have to find f prime of 0. Well, we know the derivative of e to the x is just e to the x. So f prime of 0 is e to the 0, which is 1. So the linear equation would be y equals m x minus x1 plus y1, where m is 1, x1 is 0, and y1 is 1. So we get x plus 1. That's this line right here. And so for values of x that are very close to 0, this line, this linear approximation, works well. But what works better is if we increase the degree. So notice in our second graph that we've got a second degree polynomial, this blue line. It has a squared in it. And that blue line does a much better job than the linear approximation that we started off with. So the focus is how do we figure out what is that equation for a second degree or a third degree or a fourth degree polynomial? Um, that's what we're going to be working on today. So we want to know, how do we get the polynomial? How do we actually get the coefficients that will approximate the function? Well, the important idea is that each polynomial approximation must have the same derivatives as the original function and contain the same point. In other words, around x equals 0, our polynomial function must behave the same way that our function does. So let's start doing a little bit of work here. What we're doing is we're saying we have some function f, and we're going to approximate it as a polynomial function of degree n. So this is a polynomial function of degree n. And what it's saying is that the first thing is that our function must contain the same point. And since we're looking at when x equals 0, and for this particular case, for the next couple of problems, we're only looking when x equals 0. This is saying that f of 0 must equal P sub n of 0. In other words, well, we know f of 0 because we're looking at the function y equals e to the x. So f of 0 is e to the 0, which is 1. So we know that our polynomial function at 0 must also equal 1. Good. So what else? Well, our f prime of x at 0, so f prime of 0, the derivative of my function e to the x at 0 must equal the derivative of my polynomial function at 0. So the derivative of my polynomial approximated function at 0. Well, we know that f prime of x, if f of x is e to the x, we know that f prime of x is e to the x. So f prime of 0 is just 1. So we know that our first derivative of my polynomial function at 0 must equal 1. So we've got that. And, you know, remember that what we're doing here, so we're taking a polynomial function, and the polynomial function is a string of polynomials. So it's like some coefficient plus some coefficient times x plus some coefficient times x squared plus another coefficient times x cubed. What we're doing is we're trying to find all of these subsequent coefficients. Well, given that P sub n of 0 equals 1, well, P sub n of 0, if we put x as 0 in here, is just a sub 0. So we found out our first coefficient. Since P sub n of 0 is a sub 0, and P sub n of 0 is 1, we know that a sub 0 is 1. Similarly, we know that this relationship, that the first derivatives must be equal. Well, let's take the derivative of P sub n. The derivative of P sub n of x is a sub 1 plus 2 a sub 2 x plus 3 a sub 2x squared dot 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 dot. But when we know that our first derivative at 0, when x is 0, is 1. So when x is 0, this will be 0, this will be 0, and we're just left with a sub 1. And we know that our first derivative equals 1, so 1 equals a sub 1. Now we found our second coefficient. So clearly, by taking derivatives over and over again, we'll be able to find out each one of these coefficients, a sub 0, a sub 1, a sub 2. Well, so this is what we were just looking at. We have our function, which we're approximating as a polynomial function of degree n, and this is what a polynomial looks like. And we already said, okay, the first derivative and the second derivative and the third derivative and the fourth derivative must all equal each other around x equals 0. So just to show again, p sub prime of n of x is a1 plus 2a2x plus 3a2x squared plus dot 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 dot, and p double prime of n of x would be 2a2 plus 3 times 2 times, this should have been an a3 there, times a3 times x plus dot 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 dot. And doing one more, the third derivative of our polynomial function of degree n of x is going to equal 3 times 2 times a cubed plus dot, 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 dot. Therefore, since we're looking around the point, since we're looking at x equals 0, since we're looking at making an approximation around x equals 0, and understanding the idea that the function and the polynomial approximation must have the same derivatives, we get the following. First, f of 0 must equal Pn of 0. Well, looking at this function, putting x is 0 into any of these, the zeros go away, and we get left with a relationship that Pn of 0 that a sub 0 must equal f of 0, because p sub n of 0 is just a sub 0, and these two must equal each other. Similarly, f prime of 0 must equal p sub n prime of 0. So we're looking now at this function, and when x equals 0, those go away. So we get that a sub 1 must equal f prime of 0. So if I take the first derivative of my function evaluated at 0, I find out my second or a1, my second coefficient. Let's keep going. If I take, the second derivative of 0 must equal p sub n derived twice at 0. So looking at my second derivative now, when x equals 0, this equals 0. That's all I have left. So I get that the second derivative of my function at 0 must equal 2a2, this right here. So I get that a2 must equal f double prime of 0 over 2. It's an iterative process. You start seeing what's going on here. Let's do just one more so it becomes very clear. The third derivative of my function at 0 must equal the third derivative of my polynomial function at 0. So looking at my polynomial function at 0, when x is 0, these terms all go to 0, and I get left with the fact that f triple prime of 0 must equal 3 times 2a cubed, or in other words, sorry, that's not a cubed. What am I saying? That's a sub 3. So a sub 3 must equal the triple derivative of f divided by 3 times 2. And I'm just going to add this times 1. And I'm going to go to a2 and do times 1. So we start seeing a pattern here. We have a1 is the first derivative evaluated at 0. a2 is the second derivative evaluated at 0 divided by 2 times 1. The third derivative, sorry, the third coefficient, a sub 3, is the third derivative evaluated at 0 divided by 3 times 2 times 1. And if we keep going on with this process over and over again, we develop a really nice relationship that can save us some time, which is a Taylor polynomial approximation is the following. P sub n of x, or a polynomial approximation of degree n, can be written as f of 0 times f prime of 0 of x times f double prime of 0 over 2 factorial. 2 factorial is just 2 times 1 plus f triple prime evaluated at 0 times 3 factorial, which is 3 times 2 times 1. So this is what we were developing earlier. This 3 times 2 times 1 and 2 times 1. But if we kept going, we'd recognize that it always will follow this factorial process. So this is a way that we can generate a Taylor polynomial around x equals 0. And we'll do this example problem in the next video.